Okay. Yeah, so my name is Oliver Bickerton. I'm from the University of Sydney, and I'm going to be talking to you about nanostructure enhanced CEP silicon photodetectors. Quite a mouthful, lot to go through. First thing is, what is CEP? It stands for cycling excitation process, and I'm going to get into that very shortly. First up, I'd like to give a quick overview about this talk. So initially, I'll go through a bit of background on me and the group here at USyd, talk about the motivation for the project, how does this CEP process help, why are we choosing silicon, why do we want nanostructures, and why specifically photonic crystals, what we propose, how we make it, and I'll give you some preliminary results for the work that we're doing. So this is the group working on this current project. I'm there all the way on the left. And probably the first takeaway from this is that I need to invest in a professional headshot. I don't know quite where they got that photo from, but anyway. And this research here is sponsored by the DSTG, mainly by the person whose photo is next to mine, Dr. Danik Delis. Anyway, so moving on to the larger group, our group is based at the University of Sydney, the Sydney Nanoscience Hub. We have a lot of different projects with a lot of different companies at the moment. And the main things we work on are silicon photonics, microwave photonics, and if you're in that area, there's a stimulated brilliant scattering for the light-sound interactions, photonic radar, and LiDAR. And that is our group as a whole. Getting back onto the topic though, this talk is about photodetectors, so let me get into that. First, I want to discuss why a photodetector is really important. Obviously, they're important in the telecommunication industry, lots of emerging technologies like photonic processing, fiber communications, where a lot of detector speeds are really key, in sensing and astronomy, LiDAR, fluorescent microscopy, biomedical industry imaging. They're also incredibly important. Photodetectors are really enabling us to get all these technologies off the ground and running. And even quantum technologies require photodetectors, obviously. Quantum encryptions, you need to be able to read the information you're sending, and atomic clocks, just to give a very, small dose of all the technologies that these photodetectors are sort of enabling. So that's currently what the photodetectors are allowing us to do. I want to talk about the current limitations with some of the photodetectors, specifically the silicon-based photodetectors. Now, if you're in the area, you might know that the industry is often the main contributor to silicon photodetectors in industry are APDs, or avalanche photodiodes, and single photon avalanche diodes, which are avalanche photodiodes that have been biased a little higher, as I like to say. So the current limitations are generally the high bias voltaging that you need to apply to get sufficient photocurrents. The noise which is associated with these detectors because of their internal gain mechanisms, and the additional circuitry requirements. Now this is specific to, I think, SPADs, where because of how the avalanche process works, you need an extra amount of circuitry to stop them from running away and destroying themselves. And that ultimately contributes to a higher cost. So how does the CEP process kind of help alleviate these things? The CEP process was first discovered by this group in America, and to briefly talk about how the process works, I want to first talk about how the APD process works. Now, the avalanche photodiode is often occurring in the PN junction type diode, where you have a photon comes in, you excite electron hole pairs, and those electron hole pairs are accelerated in the electric field, and they bump into other electrons, and they kind of create this avalanche effect. How the CEP process works is a little bit more complicated, but it's a little similar in the sense that, firstly, you are exciting your photons in your silicon. And then those electrons are going to travel into the amorphous silicon. And here's a bit of a counterintuitive point where actually amorphous silicon has a lot of band tail states and defect states, but actually this process uses those defect states to kind of generate a higher current. And the way it does that is as you're in this diagram, the holes come up, the holes excite another hole that's in the band tailgate of the conduction band, and they get excited by Auger excitation. And then either through tunneling or a phonon absorption, your electron will pop out and then travel back through down the slope back into your normal silicon. And this will happen continuously, and it happens also for the electron when it goes down to the bottom end of the amorphous silicon as well. And through this, we get the cycling excitation process. And so what are the key benefits to doing it this way? Okay, there we go. I think I may have gone, no, okay. So yeah, the key benefits for doing it this way, I will outline after I outline the ideal qualities of a photodetector, which are high efficiency, high optical bandwidth, single photon sensitivity, high response speed, low jitter, low reset time, low power consumption. Ooh, there's a lot of things you want. We can't have them all. So the benefits of this work is that we do get a high efficiency because of this signal gain mechanism. We can achieve single photon sensitivity at room temperature, which is a big point. We can get high speeds, and we do it all at a very low bias voltage value. And then, so now we're asking, why silicon? Well, there's a massive industry behind silicon, the CMOS industry, Intel, Google, they're all big players in that industry. Silicon is also low cost, and we want to integrate everything with silicon because that's what most of our technology is based on. This is kind of the what the optical properties of silicon is. So on this plot, we can see the absorption depth for silicon. And on the right, you can see like the typical responsivities. I think I've taken this plot from Thor Labs. So responsivity and quantum efficiencies are key indicators for the usefulness of a photodetector. And silicon, on the whole, has fairly good quantum efficiencies for the wavelengths in the visible, which is where this talk is going to be focusing. So then we've got the CP, that helps us. Now, how does the nanostructures come into this? Well, the nanostructures we want to use to try and increase the optical efficiency. So the CP is helping with the electrical efficiency, and now the nanostructures we're going to try and help with the optical efficiencies. So the way the nanostructures work is by reducing reflections is a big one, and then trying to achieve some kind of light trapping, which allows us to absorb more light in a smaller volume. And what this effectively means is that you can get a faster photodetector in the output. And then why photonic crystals specifically? Firstly, they're quite easy to fabricate, and you have high control over the optical properties through dispersion engineering. So this is just a very simple structure that we're using, and on the right you can see that there's an enhancement from the baseline. So the baseline is just, imagine if that silica block wasn't there and you just had silicon, amorphous silicon, and ITO. And so you can get some significant enhancement there. The enhancement's a little, I guess, deterred by the fact that in this specific wavelength that I'm showing you, that there's already a fairly high absorption in silicon. So obviously at higher wavelengths, you could achieve even greater enhancements, but we're focusing on this wavelength range because the people funding this project are very interested in a particular wavelength here. And then you can even increase this a little further by having a silica back reflector or doing it on an SOI structure. And so that's what's going on there. Now, this is how we make the structure. Firstly, there's some amorphous silicon deposition, which if an SEM, if you take the image, it kind of looks like that. It's a little hard to see, but there's a small layer where you can see the amorphous silicon on top. Then we do some ICP-RE etching to get the mesostructure out. We deposit the oxide so that we have good isolation, electrical isolation. Then we open up the windows using a HF or buffered HF process. Then we sputter on some ITO, which is our conductive layer, and then we etch in some nano cavities, which we then fill up with silica and etch that back. And then finally, we apply our gold contacts. And when this is all done, we can get out a chip that kind of looks like this. This is a complete packaged chip. All done at the ANFF research facilities. Now, they have great facilities, lots of good expertise from the engineers. Some of the challenges, though, are material compatibilities with tools. Maybe this isn't an issue at other nodes, but in Sydney, the Sydney node, we don't have a general etching tool, which is a bit troubling, so we can't put metals in them. And to get off with some preliminary results, first, this is our setup. We have some lasers through some mirrors, through some filters, all the way to the device under test. And this is some preliminary DC results. And you can see that we can get quite a competitive amount of gain at a very small reverse bias voltage with only 4 volts of bias. We can get a gain as high as 80,000 or a bit over 30 dB. And on the right is just the generalized photocurrent for some of those measurements as a reference. And yeah, that's pretty much it for this talk. Sorry, it's still very preliminary results on this one. But I'd like to thank DSCG for funding us and all the ANF nodes for all their help, ANU, UNSW, and the University of Sydney. Thank you. I think I went a little over time. Okay.
Thank you very much for your talk. Just slightly over time, but one question, is there one?
What is the switching speed of these CEP-based devices typically?
Oh, so how fast can the CEP, so you're talking in terms of the RF measurement?
Yes.
Yes, okay. So the CEP process, theoretically, the frequency can go well over up to the terahertz, I believe. It's a very fast process. The tricky part is getting the electrical components to be as fast. Is the main benefit. Is the main difficulty there.
Thank you very much, and good luck.
Thank you.